Hi, welcome to complex analysis. We are in the third lecture on Cauchy theory, which is going to be an extension of Cauchy's theorem for star-shaped domains. From this, we will immediately derive the so-called Cauchy integral formula. The Cauchy integral formula will exhibit the holomorphic function as a Cauchy type integral. We had already seen two examples of Cauchy type integrals. Okay, when we talked about differentiation and at two places. Okay, and as a corollary, we will immediately conclude any holomorphic function will be analytic. That is the second most basic result in Cauchy's theory of complex analytic functions or complex functions. The first being existence of local primitives, which we proved in the last lecture. Okay, so let us get started. We have a lot of things to do, but all are very easy now. But let's hope that we will get it done. Yeah, I there are some requests where to get my books. Okay, queries. So please, this is I have to correct it. ACAR. Yeah. If you want to buy a copy of my book, you can write to Techno World Publishers, who are the people who published. You can ask them how to pay the money, etc., how much, etc. Or you can also contact through this via this number and talk to them personally and get the details. Okay, right. So let us get started. So in the last thing what we did was the following. If you insist open and star shaped, and if f from u to c is holomorphic, then gamma any closed path in u, then we prove integral of f over u is 0. Sorry, integral of f over gamma is 0. This is Cauchy's theorem. Okay, now we want to extend it. What do you mean by extension? Okay, the way we want to do is the following. Okay, so we will assume u is open and star shaped, so extension open and star shaped, right? Let's assume, yeah, fix a point a in u. Assume that f from u to c is continuous and f from the open set u minus complement of the singleton to c is holomorphic. Right? Then we want to prove integral of f. Okay, let delta, maybe let's make it a point as p. So delta ABC be a triangle in u, then integral of f over t, where is 0, where t is the boundary triangle, that is the path AB plus BC plus CA. Okay, you can see this is essentially Cauchy Goursat kind of argument. Okay, Cauchy Goursat we proved if f is holomorphic on the entire star shaped domain, we proved it. Now we don't want to do that. In fact, okay, let us try to see how to prove that. Okay, so first the proof is very easy. So this is my u and this may be my bad point p, right? Suppose I have a triangle. Okay, this is my ABC. Okay, this is my triangle. All right, And so if the triangle ABC is contained in U minus P, there is nothing to prove because it follows from Cauchy Goursat. Yeah, right. So let us assume, okay, suppose P happens to be A. Okay, let delta ABC be a triangle in U, then I want to show integral f over t is 0, right? For any t, I want to prove that. Okay, so what are the possibilities? Okay, now suppose the point P happens to be A, one of the vertices, right? Now I cannot apply the Cauchy Goursat directly, even though the domain is star shaped, etc. Okay, I cannot apply. So what do I do? So what I do is the single choose a point Z and W. Maybe I will draw a big picture. Z and W, A, B, B, C. So that distance between AZ, that is the line segment, is something like 1 by n, which is same as the distance between A and W. Right? Now I form a triangle. Okay? Right? Now let us see, what I want to do is something very simple. I want to break this into 3 triangles. Okay, so I have, let me just make things clear. So that is A to Z and Z to W and W to A. Okay, so I have one triangle. Okay, the path is A to Z plus Z to W plus W to A. This is the triangle corresponding to A Z W. Okay, the boundary of the triangle. The next one, what I want to do is this one, Z to B and B to A, sorry, B to C and C to W. Okay, so the next one is Z, so Z to B plus BC plus CZ. This corresponds to the triangle delta ZBC, the okay boundary of the triangle. Okay, the third one is this. Yeah, the third one is this. So what is the third one? Third one is, okay, now Z to C. So I will start with, okay, Z to W, W to Z, Z to C and C to W. Just to make sure I am writing it correctly. This is W to Z, then Z to C and then C to W. This is the boundary of the triangle corresponding to A, W, Z, C. Okay. Now what I am claiming is, okay, the integral of f over these 3 triangles, that is delta AZW plus integral of f, not delta, the triangle T ZBC plus the triangle over WZC. I claim this path integral is same as the path integral T of ABC. Okay, right. Now let's do that. That's very clear because you just have to pay attention. Let's look at the picture already showed you. Let us look at, for example, the path ZW. Okay, this is part of this. ZW goes this way for this triangle, whereas it goes the other way around, W to Z for this triangle, right? Therefore, this fellow 1 ZW WZ, they get cancelled, right? The next one, let's look at. Okay, let's look at ZC. So for this triangle, I'm going to travel from C to Z, whereas for this triangle, I'm going to travel from Z to C. Therefore, I have this and these two cancel. Yeah. So you can see these two sides. These are the sides which are common to two triangles. Okay, they cancel out to each other because they go in opposite directions. So what I am left with is, let us look at. So this now let us come. Let me use a different color. I don't know whether I can get. Okay, this may be okay. Yeah, AZ to ZB. Okay, then BZ, that is one. Okay, and then CW and WA, that is CWWA. So what do I get? Therefore this one contribution comes to be integral of F over what are the things? AZ plus integral ZB plus integral of F, all this F. Okay, I will not write it perhaps. BZ and then integral of F over CW plus integral of F over WA, that is integral of F over triangle ABC. Okay, so pause, review, proceed. Okay, now let's look at. I am claiming that, look at these two triangles. Okay, look at this triangle. Okay, in the so integral of F over the triangle T ZBC, this is 0. Why? Because I can apply Cauchy Goursat. This triangle is contained in U. Okay, and U is star shaped and open, and F is analytic here. That's good enough for me. Okay, what all I needed was integral of F over any triangle so that the corresponding triangle is contained in U. Then it is 0. That's what we proved. Okay, so that will be 0, and similarly this triangle is 0. Yeah, are you following? Right, therefore what I get is, okay, so triangle F over T A B C is triangle of F over T A Z W. Okay, so we obtain. Just make sure you understand. So the whole triangle, three triangle, is broken into three triangles. Whatever is the point of problem, that is the point A is a problem. So we do divide and conquer trick. We isolate it. We put it in a very small place. Okay, you understand that? This is my what I keep calling divide and conquer trick. So I put it in a very small place and then try to estimate that separately. The other two triangles, okay, the path intervals of F over other two triangles are 0. Okay, by the standard Cauchy Goursat theorem. Is that okay? Right. Now this I want to estimate integral of F over integral of F over T A Z W. Remember, F is continuous on U to C and T of A Z W is compact. Therefore, mod F is less than or equal to M on this triangle T A Z W. Do you understand? Therefore, I want to use ML inequality. Therefore, it's less than or equal to M times the length. Now, let's look at the length. See this. Okay, this is A, this is Z, this is W. What is the length? We saw this length is 1 by N. What is this length? 1 by n. What is this length? I may not know, but I have an estimate for this. Okay, length of ZW is less than or equal to length of AZ and plus length of AW, right? That is ZA, distance between ZA plus distance between AW. You understand this? ZA, AW. So that is 1 by n, 1 by n. Therefore, this is less than or equal to 4 by n. And n is, okay. So this immediately shows that integral of f over t, sorry, integral of f over t is less than or equal to 4m by n for all n in capital N. Okay, sorry, modulus of this. Therefore, path integral of f over t is equal to 0. That means integral of f over t is 0. So pause, review, proceed. So we proved an extension of Cauchy Goursat under the assumption that the point at which it may fail to be holomorphic is one of the vertices of a triangle. The general case we still have to do. So let us quickly show how to do that. So what is that we have proved? We have proved extension of Cauchy Goursat right, where, so this is the thing, and my point P equal to A, B, C, right? Suppose very thing, suppose my P is elsewhere, for example, P could be here, or P could be complete in one of the sides, or it could be interior. Then what do you think I will do? I can split it like this, right? Now I can consider the triangle, okay, A, so maybe I can use as usual a different color system, and this, and another triangle, and this. So now summation of, call this as T1 and T2, then integral of f over T1 plus T2 is same as integral of f over T, right? But this is integral of f over T1 plus integral of f over T2. We had already seen this. This will be 0 because the point here is on the one of the vertices. Are you following? And remember, in Cauchy Goursat, see, just because I stated extension of Cauchy's theorem, I assumed U to be star shaped. But if it is Cauchy Goursat, I want only the triangle ABC, the solid triangle should be contained in U. That's the only condition. U is any open set, okay, and if f is holomorphic from here to here, integral of f over t is 0. Alright. So only when I wanted to extension of Cauchy, I needed U to be star shaped and open. Why? Because if f is star shaped, if it is continuous, okay, U is star shaped, and yeah, see, this is holomorphic, and f from U to C is continuous, right? Then what did we prove? For any solid triangle delta in contained in U, and integral of f over t is 0 by extended Cauchy Goursat. Okay, but we already know a proportion. Okay, our earlier proposition says if f is continuous from U to C, such that integral of f over t is 0 for all delta contained in U, then implies f as a primitive. Okay, so as I said, please go through it once again. Please go through the proof. The proof is Very easy. Okay, I took perhaps I tried to explain too much, so you may think the proof is complicated or anything. It's very simple. Okay, you keep the picture in mind. You try to sit and work out on your own. You will see how easy the proof is. Okay, it's a standard estimate, and the important trick is we again used divide and conquer rule. Remember, if you had been following my lectures on real analysis, one of the tricks is whenever there is a problem, okay, some points which are problem problem points, what do? You try to say the number of such points is very small, or if there is only one point or few points, then try to enclose them in a very small place and try to put a bound. Okay. Okay, so you should, and there is also a separate video on divide and conquer. Okay, please go through it if you are new to that kind of trick. See, this way of learning analysis will make easy for you. Otherwise, everything it looks as something new. It's not. I'm just using divide and conquer. Life is easy. Then use ML inequality. That's all the trick is. Okay, good. Okay, now this. So, right. So as a corollary, what do I have? Okay. So as a corollary. So if f from u to c is continuous and u is open and star shaped, and f is holomorphic on u except at one point, then integral of f over t is 0 for every triangle ABC containing u, right? But remember, if a continuous function has the property integral of f over the boundary of any triangle is equal to 0 for the triangle, the solid triangle containing B, then we know f as a primitive. This is what we proved. Therefore, this shows f as a primitive. Primitive in U. But if once f as a primitive in U, then integral of f over gamma is 0 for every closed path gamma in U. Okay. Please go through this. This is the kind of arguments which are very common. Please go through this argument. This is what usually I used to call, and many analysts used to call, bootstrap argument. You know, when you have a shoe, you want to tie the shoelace. Okay, what do? You insert one here, insert here, then take it out like that. Okay, so you build up on one by one. So go through the proof. So far what you have done, okay, very easy. So we said whenever I have a continuous function f, so that integral of f over the boundary of a triangle is 0, so that the triangle is contained in U, then f as a primitive, right? This has nothing to do with holomorphicity. Second thing we proved was the Cauchy Goursat theorem. It said if U is star shaped and open, right, then and f is holomorphic on U, then integral of f over any over the boundary of any triangle is 0. Okay, as long as, so remember, whenever the boundary of the triangle is because of star shaped, there a solid triangle will also be contained in U. Therefore the theorem follows. Please go through this. Do not get worried about the proof at present. This is what you, okay, you will miss the wood for the trees. Okay, just to look at the statement. What are the statements which you follow? There are series of statements, very thing. Okay, you go through them. Okay, now we proved, and from that what did we do? So once I had Cauchy Goursat, then I said on any star shaped domain, okay, then f as a primitive. That's because of first result. And from that what did I do? Since it has a primitive, okay, on any star shaped domain, any holomorphic function f, if I take, then integral of f for any closed path is 0. Yeah. Now what did I want? I wanted to extend it to functions which are continuous on the entire domain and holomorphic except perhaps at one point. Then what did I want to prove? I said integral of f over the boundary of any triangle is 0 as long as the triangle is contained in U, where U is star shaped. Open. We proved it by divide and conquer trick, right? And from that, what did you do? So it immediately said f as a, since f is continuous, such that integral of f over any boundary of triangle is 0, then f as a primitive. That we proved, right? Therefore, any function which is continuous on U and holomorphic x at one point on a star shaped open set admits a primitive. You understand? Now it has a primitive, then I know integral of f over any gamma is 0. Yeah? This is exactly Cauchy's theorem, except now I am not assuming f is holomorphic on the entire domain U. Okay, it is continuous on the entire domain and holomorphic x at one point. Okay, this is how I revise and review the results. Many people got to work only with the proof, they forget how the theory developed. Okay, this is very beautiful. It's a bootstrap argument. In my book also I will call it bootstrap argument. Okay, you build up one from the other. From here you go here, from there you come here, from there you go there. Okay, that's what you do. Learn that well. Okay, right. Let's go back. So what have we proved now? So we have proved if f, so U is star shaped and open, f from U to C continuous, and f from U minus a point to C holomorphic, then integral of f over gamma is 0 for any closed path gamma in U. This is extended Cauchy's theorem. Okay, this is what we have proved. Now the first application is the following. Okay, suppose U is again star shaped, open, right, and suppose f from U to C is holomorphic, right, and let's define a function g. Okay, g of z equal to, okay, f of z by f of z naught, fix z naught in U by z minus z naught for z not equal to z naught and equal to f dash of z naught if z equal to z naught. Yeah. Now therefore g is a function from U to C. What can you say about g? You can see g is continuous. Okay, for z not equal to z naught, that is f of z minus f of z naught. Okay, f of z naught is a constant, therefore this is a continuous function. Numerator is a continuous function, denominator is a continuous function. It's not vanishing on z. Okay, it's not vanishing on the complement of z naught, right? Complement of z naught, that is this minus z naught, that's also open anyway. Okay, so this is a product of continuous function. This is continuous on U minus z naught. So I want to worry about whether it is continuous at z naught, but limit z going to z naught of gz is exist. Okay, and what is the limit? It is f dash z naught. Therefore what is the value of g at z naught? F dash z naught. Therefore g is continuous, right? And notice that g is also holomorphic where outside this point. Why? Again for the same reason. Okay, the numerator is holomorphic, f of z minus f of z naught, z going to f of z is holomorphic, f of z naught is constant, therefore this is a okay, difference of two holomorphic functions, therefore it is holomorphic, and z minus z naught is non-vanishing outside U minus z naught, therefore 1 upon that is holomorphic, product of holomorphic functions, therefore g is not is holomorphic, right? So what do you think I can do? So I found a function g which is continuous on U and holomorphic on U minus a single point z naught. So what do you think I will be? Okay. Okay. So naturally there is a temptation for me. What is the temptation? It's a kind of itching, right? Yeah. Then you want to do something. Like as a kid, if you have a new toy, you want to play with it. So I want to play with it. What do you think I will play? Look for any close path gamma, right? Then apply it to G. What do you think I will get? So I want to apply, so let gamma be a close path. Okay. So that what? Z naught should not lie in gamma. Okay. So this is my U and this is my path and my Z naught may be outside or here. Okay. This is my gamma. It may be here or it may be here, but it should not be on the path, right? Then what do I know? Integral of f, integral of g over gamma must be 0, right? Now remember z naught, what is g? Okay, this is, if you want, this is g of z dz over gamma. Okay, this is a notation for path, but that's why I avoid it, right? That okay, right? But on gamma, what is g of z? G of z is that f of z minus f of z naught, z minus z naught, because z naught is not in gamma, right? Therefore z cannot be equal to z naught, therefore z is different from z naught, and hence g of z must be this. Therefore what do I get? Integral of f of z minus f of z naught, z minus z naught over gamma, that must be 0, right? But we know path integral is linear, therefore this fellow is nothing other than integral of f of z by z minus z naught over gamma equal to integral of f of z naught, z minus z naught over gamma. But remember, f of z naught is constant, independent of the integrating variable z. Therefore this is f of z naught into integral of dz by z minus z naught. Okay, pause, review, proceed. This is over gamma, right? Yeah. So what do you think I have proved? So let's go back. I had a function here from holomorphic and U is star shaped plus open and z naught is in U. So let gamma be a path, closed path in U, and z naught is not on the track. Then we proved f of z naught into, okay, this, whatever this thing, let us put it in a bracket, integral of dz by z minus z naught over gamma, this equal to integral of fz z minus z naught over gamma. This is called Cauchy integral formula. I call it CIF, Cauchy integral formula. Right? So I almost got f of z naught as a Cauchy type. This is, notice that this is a Cauchy type integral. Yeah, this is a Cauchy type integral, right? So I got f of z naught as almost like a Cauchy type integral, except I don't know what this is. What is this? Right? And this is where again you have followed my earlier lecture. You know that if gamma is a circle of this kind, let us say for example, okay, some circle a plus r e power I t, okay, then we have seen that, okay, 1 by, okay, w minus z over gamma dw is 2 pi I if distant, that is mod z minus a, is less than r, and equal to 0 if mod z minus a is greater than r. We have seen this. Yeah, and at that time we call this as a winding number. Okay, so the integral 1 by 2 pi I integral of dw by w minus e over gamma, we called it winding number of gamma around z. So that shows how many times gamma winds around z. Okay, that makes sense. Okay, this we have proved it. Okay, this has meaning only in the case of circle. Please understand. Okay, that okay, based on that geometric intuition, for any closed path gamma, I want to define this as a winding number. Please understand. So if gamma is any closed path and z0 is not in gamma, then 1 by 2 pi I integral of dw by w minus z0 is n gamma z0, and it is called the winding number of gamma around z0 and is denoted by n gamma z0. Okay, therefore Cauchy integral formula, it becomes, okay, right. So let us go back. So what did I do? So they said that integral of dw by w minus z, w minus z0 over gamma into f of z0 equal to integral of f of z or w minus z0 over gamma. Go through this. This is what we did, Cauchy integral formula. So this, okay, and what is this? If this is 2 pi I times n gamma z0 into f of z0 equal to this, right? Therefore f of z0 equal to n gamma z0 into f of z0 equal to 1 by 2 pi I integral over gamma of f of w by w minus z0, as long as z0 is not on gamma. So pause, review, proceed. I have not done anything. Please understand, I have not done anything. I simply, this unknown integral, this object, okay, I decided to say this is 2 pi I times n gamma. Okay, this is just a notation. Instead of this notation, if this is an integral, I have to evaluate. Okay, I pretend, okay, it is some number n gamma, complex number n gamma z0 times 2 pi I. Okay, that's it. So what I have got is n. So let me recall. Therefore n gamma z0 equal into f of z0 equal to 1 by 2 pi I integral of f of w by w minus z0 for every z0 not in gamma, that is for every z0 in u minus gamma, right? So remember, but again there is still, I have just a kind of something which I don't know about integral. I just started calling n gamma z0. So what do you think I would, this is over gamma, this is a path integral. Okay, what do you think I should do now? Look for a gamma which is simplest so that I can do that. You understand that? Remember, this is true for every z0, therefore let me write it in slightly different way. N gamma z f of z equal to 1 by 2 pi I integral over gamma of f of w by w minus z for all z in u which are not in the trace of gamma, track of gamma. Okay, and what is the gamma for which I know what is n gamma z? That we know. Yeah, right. So let us look at. So now fix a point A in U. Yeah, and let us look at a BAR, so that BR is contained in U. Right. Now choose any R. Right. Let us look at gamma R of t equal to A R e power I t 0 less than equal to t less than equal to 2 pi. So why I am looking at this? I want to look at simplest gamma for which I can figure out what this really means. Okay, right. Are you following? Then what we know? Then I know n gamma r of any z equal to 1 if distance between z and a is less than or equal to 0 if z minus a is greater than or. Right? Are you following? Yeah. Therefore, for such r, what do I have? So n gamma, let's go back to this. So now for if gamma is gamma r, then for every z, okay, which is in BAR, okay, what do I have? So I have n gamma r of z into f of z is 1 by 2 pi I integral of f of w by w minus z over gamma r. This is 1 if, okay, z lies in B0, BAR. Okay, right? So I have this, I have some A, and look at, this is my R, look at any Z here, okay, then I have, okay, now let us look at what do I know. So let us define a function g of z equal to 1 by 2 pi I integral over gamma r f of w by w minus z, where z is in u minus gamma. And remember, f is a continuous function, f is holomorphic on all of you, therefore f is a continuous function. Okay, and z is not here, then we know this is analytic. Do you remember? We have proved it. This is a Cauchy type integral. We have seen that defines analytic function on what? On u minus gamma. Right? But are you following? Yeah. In particular, what is g of z? G of z is nothing other than f of z for z in BAR. That's what quotient by Cauchy integral formula. Right? Therefore, f is analytic in BAR. Yeah. In fact, it is actually we have seen that it could be a power series. Yes. So we have proved so what did Cauchy integral formula say? The holomorphic function is given as a Cauchy type integral. So if I choose my closed path gamma suitably like a circle with standard parameterization, then I know what is the winding number. Therefore, I know f of z for any z enclosed by the circle, okay, is equal to 1 by 2 pi integral of fw by w minus z. And I know such functions defined by Cauchy type integrals are analytic outside the path, right? And notice that what is this path gz? the function gz is fz for z in bar. Outside it is 0. Do you understand why? Because there is an n-gamma. Okay, let's not worry about. So this is analytic. So what I have shown? So I have shown that my function f is analytic for anything. So you start with a z and you put an open ball around that. Okay, then you can express this. Okay, please understand. These are the subtle points you should know. These are all very easy, but it will be good. You think on your own. So you give me, okay, any z in u, and of course I am assuming this doesn't look like star shaped, but I am assuming it's open and star shaped. Okay, then you put z in some open ball. Okay, make it capital R if you want. Then choose a small r, right? And for every maybe you fix an a, okay, a, and for every z, then I have f of z in bar is going to be 1 by 2 pi I gamma r f of w by w minus z, so that whenever z is in bar. So you follow that? Therefore f is analytic here. Yeah. So what do I guess? Therefore f is analytic at each and every point. Therefore f is analytic on u. Right. So we have proved the second most basic fundamental contribution of Cauchy to the study of holomorphic functions. One is any holomorphic function admits local primitives, and any holomorphic function is analytic. Why it is analytic? Because any holomorphic function is represented by a Cauchy type integral. In particular, Cauchy type integral over a circular path, for which I know what is the winding number. Therefore, I can conclude it has to be analytic. And how did I conclude Cauchy integral formula? By Cauchy's theorem, extended Cauchy's theorem. If I have a continuous function which is holomorphic except at one point, then integral of such a function over any closed path is 0. Of course, star shaped, open, etc. Yeah, right. And how did I prove that? That's what about 30 minutes ago I recounted. So now don't worry about the proofs. Go through the systematic arguments, main results. Okay, what are the main steps we arrived at these two results? Okay, that will be the best one. That will give you an idea. After that, you go through the proof line by line, check and master it. I hope all of you enjoyed. Okay, there are a lot more consequences. Any study, any property of holomorphic function, local property of holomorphic function, okay, the main tool for us will be Cauchy integral formula hereafter. You will see that as we go along. So, but before that, please go through all these arguments. Make sure we will give applications of this in the next lecture also. Take care, stay safe.